Hey, I'm Joe Palney from the Algorand Foundation, and in this video, I'm going to be showing you how to use smart contract storage with Beaker, and specifically, I'm going to be showing you the differences between global, local, and the new box storage that was added in AVM 8, and why you might want to use box storage. First, I'm going to start off with a quick presentation highlighting the different storage types, and then we'll jump into some code showing you what they all look like. Before I go into the storage itself, I want to cover the minimum balance requirement concept on Algorand. This is a layer 1 feature that assigns a minimum balance that every account on the chain must hold. To start, every account has to hold zero point 0.1 algo, so if you have a zero balance account and try to send it anything less than zero point 0.1 algo, the transaction will fail. And if account tries to do any transaction that results in less than zero point 0.1 algo, the transaction will fail. The transaction fails in any sort of case if it would result in the MBR going below or in the balance going below the MBR. The only exception to this, though, is if the account explicitly closes out their balance. So this means if an account wants to bring their balance to zero, they can send all of their algo to another account. And on the layer 1, the MBR essentially serves as a data rental. Increase in on-chain data results in an increase of MBR. So anytime you're doing something that requires more data, such as creating a smart contract, the MBR of your account is going to go up. So with that out of the way, let's talk about the different types. So the most common type of storage, especially before AVM 8, is called global storage. This is 64 key value pairs per contract, and each key value pair is limited to 128 bytes. So this means the size of the key plus the size of the value has to be 128 bytes or less. The global storage can be read by any app on chain. So this is completely publicly scoped information. And the MBR for the global storage is funded during the app creation by the person that created the app. So when you create an app that uses global storage, your MBR will increase proportional to the amount of global storage used. And that's a key thing to know about global storage, is that when you create an app, you have to define how much storage is used at creation. You can't dynamically add storage as you go. Local storage is similar to global storage, except it's per account. So you have 16 key value pairs per account. This means if you have a smart contract that has 1 million users, each of those million users can have their own 16 key value pairs that is associated with their account. Much like global storage, it's 128 bytes per key value pair, and it can be read by any app on chain. The difference is that the MBR is funded during an opt-in transaction by the end user. So the end user has to explicitly do a specific transaction to say, hey, I want to use local storage for this smart contract. And when they do that, their MBR will increase proportional to the amount of local storage used. And much like global storage, how much storage is used in local storage per user has to be defined at the creation. Like I said, accounts have to explicitly opt in, and one thing to note about local storage is that it can be cleared by the end user at any time. So you never want to save critical information in local storage, because it can always be deleted at any time. And this is even if you have logic in the clear program, which is the program that is executed when a user wants to clear their state. Even if that logic fails, it'll still wipe the local storage. So there's no way to get around the fact that end users can delete their own data. Now in AVM 8, which just released a couple days ago as of this video, we have box storage. And box storage is quote unquote unlimited name storage segments. I say unlimited, but of course there are some limitations into how high you could really go, but it's uncapped. Unlike storage, global storage, which is 64 key value pairs, here you can have much more than 64 key value pairs. And each segment, you can have up to 32 kilobytes in a specific box. So it's kind of like a key value pair where you specify the name of the box, and in that box there can be 32 kilobytes of data. The other major difference with box storage is that it can only be read by the app itself. So if an app creates a box, no other app can read that box unless it does a inner transaction to this smart contract that explicitly returns it. But on chain, no app can read it. So the data can be, you can have like a fee that blocks access to the data, and you can only see the data if you pay. Of course, this only applies to on-chain. Anyone off-chain using like an indexer or an explorer can see what this data is. It just changes how it's accessed on-chain. And what's also different about boxes is because you can have an unlimited number of keys or number of boxes, the MBR is funded during the box creation itself by the contract itself, and it's proportional to the box size. So, for example, when you have a smart contract, you can create it and it'll say, use 0 global storage. You just pay the MBR for the app itself. But as you add boxes, you need to pay for those boxes. And I'll show you what this looks like in the code, but you basically need to fund the smart contract itself before you create the box so it can cover that MBR requirement. So this is going to be a very simple voting application. It's not actually like functional in any real sense of the word. It's just a very simple record user votes. So here in our common.py, and by the way, I'll share the link to this repository in the description of the video. So here in this common.py file, we define our vote application. And this is going to be an application that is used in all of our different implementations. In our files here, you see we have a box implementation, global storage implementation, and local storage implementation, and they all build off of this vote application. So the first thing we're going to do is we're going to save a proposal in global storage. And I should mention that we're using Beaker and PyTeal. If you aren't familiar with these tools, check out the Greenhouse Hack pre-programming playlist where we have videos covering how to build with Beaker and PyTeal. So I'm going to assume you're vaguely familiar with Beaker, but I'll be going over the storage concepts explicitly here. So here we create our smart contract class called vote, and then we create our application state value. And what this is doing is basically saying we're going to have a global key called proposal, and it's going to save some bytes. And this is going to be saving, right? We can think of this as, let's pretend this is a DAO and the end users are voting on some proposal. We're going to save the proposal here in global storage. So our create function, all we're simply going to do is hard code the proposal to be buy NFTs question mark. So, theoretically we're voting on whether we think the DAO should buy NFTs or not. Then we have our opt-in function. This is used in local storage. And what we're doing here is just returning approve. So this is basically saying anyone can opt into the contract, and that's fine. Now, finally, we have our submit vote function. Here, it's just rejecting because this is the superclass of the application. In our subclasses, we're actually going to be implementing what this should actually do. Then in our code here, we go over basically creating the application and actually submitting the votes itself. But before I go over that, I want to go over all the different implementations using different storage type. So kind of the default de facto storage type that most smart contracts, especially before AVM 8, use is global storage. So here we have our global vote contract, and this inherits from the vote contract that we wrote in our common.py. And we are defining this votes reserved application state value. And what this is basically doing is saying, hey, we want to have this group of global state keys that signify votes. And these votes are going to be UNT64s. And so here we're saying we're going to have UNT64s in global storage, and we want to specify a maximum of up to 63 keys. And if you remember, the reason why we have to specify max 63 is that in our common.py, we already have a storage or already have one global storage key. So now we're limited to 63. And this, because the max is 64. And this highlights kind of the first problem with global storage is you're really limited in terms of the number of key value pairs you can have. So when you need to use global storage for important things like the proposal here, you're limited into how much dynamic global storage you have. Here we only have 63 keys to work with. And our submit vote function is where we'll actually see that get used. So here the submit vote, it's just taking in the vote, which is a Boolean, true or false, yay or nay. And here what we're doing is setting the transaction.sender key. So in our global state, the transaction sender address will be the key, and then the value that we're setting here is just going to be the value of the vote itself. So whether in global state, this will basically say, does this address vote yes or no? And then approving it. So the actual functionality here is very simple. Again, this is just an example implementation, not an actual functional implementation that you would use in the real world. But what we're doing here is basically just saving this address, voted this, having that all in global state. And then we have, I should mention, some code down here that basically writes out our teal. So to run this, I can run global.py. It's going to print out the app ID, and then it's going to run the submit votes function, and it's going to error out here. So if I look at what the error was store integer count 64 exceeds schema integer count 63. And this is basically saying, hey, you tried to store too many global storage keys in this contract. And this is inevitable. If we look at our common.py code, what we're doing here is we're opting in, or we're interacting with the contract 100 times. So we're generating 100 different accounts to generate this code and to call the contract and to generate those key value pairs. And eventually, once we hit the limit, it's going to error out. So to go over what this is doing, it's basically generating an account, and then doing specific options specific to what contract we're interacting with. For global vote here, we're just initializing it with the account minimum balance plus the fee, and then calling our vote with a vote true, and then printing out the state that we're saving. So here for a global state, you can see that in one simple call, if I scroll up here, you can see all the addresses and what they voted here. Everything's just hard coded to true. You can see this address voted yes, this address voted yes, so on and so forth. So accessing global state is very easy. It's just one simple call, especially with Beaker. We're just calling our get application state function, and we get all of our application state value in one call. But again, that's only useful if you're using less than 64 key value pairs. As soon as we hit that limit, our smart contract's going to error out, and we have to look for an alternative solution. So the next solution here, instead of using global storage, we can use local storage. So here we initialize our local storage, very similar to global storage, except we don't need to specify max keys because we are just saving the vote. It's just one vote key value pair per account, right? So we don't need to specify more than one key here. So what we're doing, create local vote, inherits from vote, and in our submit vote, what we're doing is setting the votes of the transaction.sender. So here in our global state example, this was saying use the key transaction.sender use the key of transaction.sender in the global storage key value pair. But here we're saying we want to access the votes storage of the transaction.sender and setting the vote to vote.get, which is the value that they pass in. So what this is basically signifying is that we want to access the local storage of the sender and then put in our vote. So if we were to run this, we can run local.py, spit out the app ID here, wait for it to run, and then we can query over all of our local state. So if we go to our common.py and see what we're really doing here, you'll notice that we are iterating over all the addresses. So when we generate the accounts, we are adding it to this adders array, and we use that then to iterate over the addresses and call this get account state function. Now, this is important to note because the key here is that you need to know all of the addresses that have local state. There's no there's not a simple call that just show me all the local state for every account that is opted into this account. And the reason being, like I said, you could have like a million end users interacting with a given smart contract. So you would need to manually keep track of all the addresses that have local state. And depending on your use case, this might not be desirable. For example, something like voting, you want to make it as easy as possible to see what people are actually voting for. So using local state, well, you could technically go to an indexer and walk all the different accounts that have interacted with a smart contract, seeing if they're opted in, and then getting the local state and doing a bunch of stuff, manually. You pretty much, if you want to avoid doing that, you pretty much need to know all the addresses that have opted into the contract. And so you need to source this data from presumably some trusted source. And obviously that goes against kind of the blockchain ethos, and it can be unpractical to store all the different accounts and some separate data structure outside your smart contract. So that's the main limitation with local storage. And if the other limitation, as I mentioned, if we're using local storage here, we have to fund the account with additional minimum balance requirement because they need to opt in to the local storage of the application itself. So they need even more money. If you remember, or more algo. If you remember, for our global vote, we just needed 100,000 algo. Here we need pretty much like 2.5 times that, or 2.3 technically, times that value, just because we're using local storage. So one of the constraints of local storage is that it's more expensive for end users. So now the other thing we have to do is do this explicit opt-in call. So before an end user can interact with this application and actually send their vote, they have to send an additional transaction saying they want to opt into the application. So that's kind of the downside of this, right? It's more expensive to use local storage than global, and you have to explicitly opt in, which in a lot of cases can add a user friction, which is undesirable. So that is local storage. Finally, let's take a look at box storage. So what box storage looks like in PyTeal, or in Beaker, I should say. Again, having box vote inherit from vote. And in this case, we are using this mapping class. And what this is basically doing is we're saying our votes variable here, or property of this class, is going to be a mapping of addresses to bools. So same data structure as always. We're basically mapping, hey, this address voted this, and we're using this mapping construct to say what the actual types are. So that's one of the nice things about boxes and Beaker, is that you can very easily specify the types of the values that you're saving. And then here in our actual submit vote function, again, passing in a Boolean, and we're saving it a mapping of the transaction sender. So this is going to be the name of the box, or the key of the key value pair for the box. And then we're setting the value to vote.get. And the caveat with boxes is that they can only store bytes. They cannot store integers. So we have to convert this Boolean, which at the low level is an integer. We have to convert it to a byte array or byte slice using this I2B function. And then if we go and run it, what we'll see here is again a mapping of addresses to the values. Right now, the box functions don't decode the data for us. What we can see here, this is going to be the address itself, and then the value, this is just a 1, because if you remember, we hard-coded it to true. So again, much like our local and global storage examples, we have a mapping of addresses and what their vote was, this time saved in boxes. And let's take a look at what that required in terms of actually interacting with the smart contract. So the address itself, the end user itself, still only needed 101,000 micro algo or 0.101 micro algo in their account before interacting with this app. But we also needed to fund the app with this amount of micro algo to cover the box MBR. So if you remember, when we create a box in the application, the MBR for the application account itself is increased. Thus, we need to fund the application with that amount in order to create the box. So if we go down here now for actually reading that information, what we can do is we can query the address or query the application to get all the box names. So this is different from the addresses, because if you remember the addresses, we had to explicitly save ourselves, whereas now with the box names, we can just query the chain. So again, the key here is that we don't need to know the addresses or the box keys ahead of time. Here with boxes, we can just use this get box names function to get all the boxes in the contract, and then we're iterating over those and then getting the box contents to spit it out, and that's what we're seeing here. So to summarize, with global state, you only need to have the accounts be funded with this 0.1 algo or 0.101 to cover the fee algo to interact with the contract, but you run out of storage once you have more than 64 votes. With local storage, the end users need to have more algo in their account, and they need to explicitly opt in, which adds some friction when interacting with the contract. And then for boxes, they still only need 0.101 algo, but somebody, it can be the end user, the application creator, or just any random account, needs to fund the application itself. And that's for actually interacting with it. And then after the fact, in your front end, for example, global state, it's just one simple call, but again, you'll hit that 64 key limit. Local state, you need to know all the addresses one way or another. If you have some data structure where you can save it, off chain, for example, that could work, but again, that's centralized and not too great. The alternative is kind of just a brute forcing a search. We're finding all the accounts that are opted into this account or opted into this application. So not a great solution. And then finally, boxes, we don't need to save any data explicitly. We can just query the application to get the names and then iterate over those to get the values. So boxes is really kind of the best compromise where we don't need to do that explicit opt-in. Yes, there is this additional fund that needs to be sent to the contract itself, but this can be done by anyone. So if you're the app developer creating an application that wants to reduce end user friction as much as possible, you can fund this yourself, or you can ask the end user to fund it, whatever you find is more appropriate for your application. And it's kind of like a middle ground between global and local storage in terms of limitations, but you have unlimited key value pairs, which is really big. And the thing I didn't show you in this example is leveraging the fact that boxes have up to 32 kilobytes of storage. So in global storage and local storage, you're limited to 128 byte key value pairs, or 128 bytes between the key and the value. Boxes, you have 32 kilobytes total. And what this basically means is you can have large data structures. So you can have like lists, maps, stuff like that in a box itself. And the only limitation on that is you need to specify which boxes you're accessing. So if we go over and look at our actual application call, you'll see that we specify we're going to be accessing the box of the address on our application. So that is a limitation in terms of interacting with a smart contract. but in a decent implementation, it should be easy to figure out which boxes you need to access. And at some point in the future, we will have simulate endpoints where you could basically run a mock run and determine what boxes you need to access as well. So this limitation is not too bad. The thing that's worth mentioning is that each reference like this is adding 2 kilobytes to the amount of data we can access. So, for example, if we had a box that was 2 kilobytes, this is all we would need. If we had a box that was 4 kilobytes, we would have to do something like this, where we're basically passing this tuple twice to signify, hey, we want to reference two different, or basically we want to reference a total of 4 kilobytes, 2 kilobytes each with each reference. And when we access the data itself, you can then iterate over the box in 4 kilobyte chunks. So that's the other thing to mention with block storage. If you have more than 4 kilobytes, you can still only read 4 kilobytes at a time due to the limitation on the stack size in the AVM. But this is all advanced stuff that you'll figure out as you start building. Also in the description will be the box article talking about all this stuff in depth, giving a nice summary of global versus local and box as well. But this is just an introductory video into what box storage with Beaker looks like and why you might want to use it. The key is just using this mapping value and then interacting with it just like the other storage types that we previously had. For Greenhouse Hack 3, if you're watching this in right now, it's December of 2022. Greenhouse Hack 3 will be starting December 20th, I believe, or 21st maybe. And one of the challenges there will be using box storage. So this is a good place to start. And again, the repo will be in the description. If you have any questions, feel free to reach out to me. I'm on Discord as Monopoly Man, or you can email me, joe@algorand.foundation, or I'm on Twitter, joe_Polny. Reach out to me however you can, and I will be happy to answer your questions. Until then, good luck in the hackathon if you are participating, and if not, hopefully you still found this video useful in learning how to use box storage with Beaker.